We've looked at already qualitatively what happens as we change the size of the rod. We did that using a PhET simulation. So we know what to expect, but what about with the math? So what happens, so we've already found our expression for the electric field around a long rod, and it depends on the length of the rod and the charge and how far away we are. If we were going to draw our picture, here's our long rod. We know that all y components will cancel because everything from the top half will point right and down. Everything from the bottom half will point right and up. The up and down parts cancel. The resultant electric field would point to the right. But what happens is that rod gets smaller and smaller. So if we make it a little smaller, we still get that cancellation and it points out. And make it a little smaller, it still points out. Make it smaller still, and it looks exactly like a point charge. So in each case, it keeps pointing away, but as we make it really small, it looks like a point charge. And we saw that with the PhET simulation. How about the math? Does the math back that up? So let's look at our equation here. We see we have an L in our denominator. So what happens if L approaches 0? That means that our electric field is K times Q. And here this is an equation for the magnitude of the electric field. Over x times the square root of x squared plus 0 over 2 squared. So that term is gone. Square root of x squared is just x. So that gives us kq over x squared, where x is our distance from our charge to our point. So yes, the math backs it up. This looks like a point charge. So that's one extreme. What about the other extreme? What if our rod gets really long? Then what can we say about the electric field strength? So let's go from that finite-sized rod, and let's go to a really long rod. And you can imagine this going out in all dimensions, or not in all dimensions, in both directions, up and down, until it's infinitely long. So for the shape of the electric field, we're still going to get that cancellation, and it's still going to point out. Okay, so the electric field will still come out this way. And that's also what we saw in our simulation, that the electric field is going to come out everywhere. But what about the math? What does the equation tell us for the expression for the electric field as it gets very long? And very long means that our L goes to infinity. So we're going to look at our equation for electric field here, and we're going to ask what happens to this expression as L goes to infinity. So what happens to our denominator as L gets really, really big? So let's start to look at that. So our goal is to find what is E of x as L goes to infinity. And we'll use this sort of treatment from time to time in this class, so we'll think about behaviors in different ranges. So let's start. So inside the square root term, we have x squared plus L over 2 squared. So that's what we have right here. The next thing I'm going to do is take my L over 2 outside. So that's L over 2 squared outside of x squared over L over 2 squared plus L over 2 squared over L over 2 squared. Okay, and the reason I'm doing this is because I want to get an expression I can work with. So now this goes to L squared over 4 outside of, I've got 1 over 2 squared in my denominator. That becomes a 4 in my numerator. Got my x squared in the numerator, so that stays in the numerator. Got my L squared in the denominator, that stays in the denominator. L over 2 squared over L over 2 squared, of course, is 1. Okay, so now in this expression, I see that I've got 4x squared over L squared. What do I know about this? Well, if L is very big, then this whole term is approximately 0. So this guy goes to 0, and that's because L is so much bigger than x. So now this whole term is approximately equal to L squared over 4. So what that tells us is that in our denominator here, if L gets really big, this x squared is not very important, okay? This is the dominating term, and we showed that because x over L is pretty close to 0 when L is really big. So let's put this expression in for our denominator up here. So then E of x, when I put in this approximation, is Coulomb's constant K times the size of the charge Q over x times the square root of L squared over 4. Square root of L squared over 4 is L over 2. Got a 1/2 in the denominator, so that 2 can come up to the numerator. So I get 2kq over x times L. You might recognize this q over L as the charge density, linear charge density. So if our rod is very long, the electric field depends on the charge density of the rod. If our rod is positive, it points away. If our rod is negative, it points towards. So this is an interesting result. When we come to chapter 24, we're going to revisit this topic, and we're going to find this exact same expression, but we're going to use Gauss's law. To set the stage, just remember how much work it took us to get right here. We had to think about our rod, we had to think about all the little bits of charge, we had to add them all up, we had to do an integral to come to this expression, then we had to find it as L gets very long. Keep in the back of your mind that when we get to chapter 24 and do this as a Gauss's law problem, it's basically a three-line problem, so it's really fast when we get to Gauss's law, but this gives you the foundation for understanding where all that comes from.